Okay, I think that's good now. Okay, sorry. Okay, hello everyone. My name is Hugo. I'm very glad to present here at CODASPY 2022. The paper we're going to talk about today is ProSPEC, Proactive Security Policy Enforcement for Containers. This is a conjoint work between my fellow colleagues at Concordia, Montreal, and some researchers from Ericsson Security Research Canada. First about the outline. So we're first going to talk about the motivation of this work. We're going to see like the key idea and our contribution. We will then have a look at the methodology that we use, have a look at the implementation, the experiment, and of course some concluding remarks. I first like to talk about what is the background of our work. So we talk here about cloud native environments, and when we mean cloud native, we mean a cloud infrastructure on which containers are running. So containers are an operating system virtualization thing. So as you see here, the containers, they run on top of the operating system. So you don't need exactly to know how it works, but you have to think about it as like a little bit like a VM, but very fast. And so they are very useful nowadays in cloud native environments and every service-based environment. So as I said, containers are the product of operating system level virtualization. And the last aspect that I want to introduce you to is the container orchestrator. So the container orchestrators such as Kubernetes, which is the mainly used one, their role is like to manage and maintain the container in the cloud. Okay, I also want to introduce you about security in Kubernetes. So as you see here, we have what we call a cluster. So a cluster is composed of a cloud of nodes, which are physical machines. And on each node, we run some pods. So the pods are like kind of equivalent to the containers. The main object we're going to talk here is pods. And so we have, of course, the master node, which contains the container orchestrator itself. And the main aspect of security is what we call an admission controller. So admission controllers allow you, they allow you to enforce some security policies in your cloud. So for instance, any request, for instance, if we want to create a service in our cloud, any request will first go through the admission controller, and this is where you can enforce some policies. After that, the request will be either denied or accepted, and the container orchestrator will enforce that request. So the main tool to do admission control in Kubernetes is called OPA Gatekeeper, and we found out during the research that this kind of tool, they present some limitation, as we're going to see right now. So the first motivation for our work is that the admission controller, the existing admission controllers such as OPA, they cause significant delay due to their reactive nature. So when someone like an attacker wants to perform an illegal operation on the cloud, the operation is gonna go through like the admission controller at runtime. And so, for instance, here, if the attacker wants to hijack one of the pods by creating a service that has the same IP of the pod, this is called CV 2020-8554. This is a known vulnerability in Kubernetes. The policy we enforce in OPA Gatekeeper needs to verify that any service creation has a different IP than the existing pods, because otherwise we're going to hijack that container. So the policy verification delay that is needed to enforce such policy, we have two things. We have data collection, because we need to actually gather the different IPs of the pod existing in the cluster. And after that, we need to verify this IP against the new IP that we want to create. So all of these delay, they grow linearly with the size of the cloud. And if you have very big clouds, like we have more and more containers in the cloud, it can be completely overwhelming in some cases. The second issue we have is that if we want to actually reduce that delay, we can use something that is called data replication. That's something that exists in OPA. And this mechanism actually introduces some security breach in the cluster. So we found a CVE during our research scored 5.3. And I'm going to try to explain quickly how it works. So the data replication mechanism aims at trying to gather the data we need in advance, replicate it inside the admission controller, and when we need it, it's already here. So we don't need to actually collect the data at runtime. We can do it in advance, and so it's going to be faster. The only problem is that there is a slight delay between the moment you actually create the resource in the cloud and the moment when you actually replicate it into the admission controller. So for instance, if an attacker creates a pod with such an IP here, the request is going to be verified, it's going to be accepted because there is no issue for now, and it's going to be created in the actual cloud. There is a slight delay in which OPA needs to replicate that resource for him in order to reduce the verification delay. But if the attacker is fast enough to create new services with the same IP before the resource is replicated, that request is also going to be verified, but it's going to be verified against nothing. So that's basically a race condition or like an inconsistency issue that allows the service to be created, and the policy here is basically bypassed. We have proof of concept on GitHub. Okay, so following this motivation, we're going to see the key idea of our work. So the key idea of our work is to do proactive verification. We want to perform the computationally intensive verification step in advance. It means before the event actually happens. And so we keep the runtime enforcement step very lightweight with a practical response time. So to illustrate that, here is how classical reactive solutions work. When we have the current event, we're going to do the verification, then the policy enforcement, and we have response time. But for us, we're going to predict what the current event, what the next event is going to be. And so when we have the past event, we're going to actually start to verify before the event happens. And when the event actually happens, we just need to do the enforcement. And so the response time is very, very slow. Very fast. So to do so, we use the historical data that are the events that were that happen in the cloud. We generate some event predictive model, and then we actually store the verification data that we pre-computed in advance in some database that we call a watch list. Our contribution, so we are the first work offering proactive security policy enforcement at runtime for containers. And we enforce, we ensure an enforcement with a practical response time, so around less than 10 milliseconds for 800 pods, compared to like more than 600 milliseconds for existing work. We studied the dependency relationship among container management events, and we built a predictive model of container events. We are integrated with Kubernetes and other legacy policy enforcement engines, such as OPA, the gatekeeper that I was speaking about earlier. And we disclosed a CV during our research. Let's see for the methodology. I just need to make sure the time is correct. Okay. So for the methodology, we are basically, we have two steps. We have the offline step and we have the runtime step that I'm going to detail right now. For the offline step, the first part is like, of course, to build the predictive model. So for that, we first collect the logs of the Kubernetes cloud, and we process them and we extract meaningful sequences that lead to events we know are going to have a security issue. That we call critical events. So for instance, the service creation that I showed you earlier, which is something that can lead to policy bypass. Then, of course, we need to create the actual predictive model. So we use Bayesian network to actually infer the predictive model with the events, and we save it into a database. So here is an example. We have some raw logs from Kubernetes here with some verbs and some resources, for instance, create pod, create service. We identified an event. We identified the sequences. So each sequence ends like with the critical event, for instance, create service or patch service, which are events that are dangerous for us. We cut the sequences. So now that we have sequences, we can create like the main nodes of our predictive model. We build the immediate transition between the different events. We use BFS to build also the non-immediate transition in order to make sure that we don't miss any event. And we learn, as I was saying, the probabilities of such event transitioning using a Bayesian network. For the runtime step, we actually have two main things here. Three main things. Of course, we need to intercept the event that actually happened in the Kubernetes cluster. So here, based on that, there's two cases. If the event is non-critical, so if it's a normal event, we're gonna proactively verify what that event will lead to. So first thing, we need to predict the future event. Then, so of course, using the predictive model that we built earlier, we're going to collect the data in advance in the cluster based on that event. And we're going to build the watch list, which contain the verification results that will be used if the critical event that we predicted actually happens. So yeah, in the end, we have the watch list. On the other hand, if we intercept an event that is actually critical, this is where we're going to use the watchlist results that we pre-computed in order to verify it first and take a decision, either allow or deny based on the result that we pre-computed. Here we see an example. Maybe I'm going to skip that because we don't have time. Just going to go through it quickly. So we have a security policy that is the same as I was explaining before. We don't want services to have the same IPs as pod. This is, as we saw, this is dangerous. Two critical events, create service, patch service. When the attacker when someone first creates a pod, it's going to be accepted because it's not critical. We predict the next event, which is going to be create service. And in the watch list, we can actually put the IP address of the pod that is created and that we can use later on. When the attacker comes and create a service with the same IP, we don't need to collect anything. We just need to look at the watch list, compare it to like what is like the IP of the service. If it's the same, of course, it's going to be denied. I also have some more example, but I'm going to skip them for the sake of time. Let's see quickly the implementation and the experiments. So for the implementation, we use Logstash and the Kubernetes audit logs to collect the Kubernetes logs. We process them with Python, and for the for the model building, we use PGMPy. So that is a Bayesian network library. And we use the maximum likelihood estimation in order to have the probabilities of such event transitioning. On the runtime step, we intercept the event with a server that we made, like a kind of a proxy. We use Flask. The verification is done with our code using Python. And for the policy enforcement step, we actually reuse OPA Gatekeeper, but like vanilla, without any additional features. We just use it because it's practical and it does its job. The database is just an SQLite database. Let's go through the experiments. So of course, first thing we want to evaluate is how good we can predict the events, if we are actually predicting correctly or not. You can see here on the left side figure, there is a maximum of accuracy for a given threshold. I'm not going to expand on what the threshold is, but this is an input parameter of our program. And as a maximum accuracy, we reach 98.4. which I think is enough to know that we actually predict the events correctly. The model training is, as you see here, for 10,000 sequences of historical events. We only take around 4.5 seconds to build the model, which is fine, because that's just like the event building step is a step that is only run maybe once a day or twice a day. You don't need to run it a lot. That is a step that is done offline. Now for the runtime enforcement delay, so this is where I was saying we have two different policies on which we evaluate our work. I'm just going to detail the left side figure. This is the policy that I talked to you earlier. So you can see on the two upper plots, you have the OPA gatekeeper policy enforcement time. So you can see that it goes as high as 600 milliseconds, and our work stays almost constant below 10 milliseconds, because we don't need to do any linear step. We just do everything in advance. And so this is why we can just keep an array search, which takes like basically no time. It takes around 10 milliseconds to enforce. The second policy, you can see that it's less complex. So OPA gatekeeper does around the same time as us, but we still like stay almost constant around 10 milliseconds, and it goes, I guess, 30 milliseconds. Just to precise, in the 5G specification, you may think that 600 milliseconds is not that high, but for reliable ultra low latency scenarios, 600 milliseconds, for instance, in an autonomous vehicle, that's a lot. You cannot allow you to have like 600 milliseconds of delay. Okay, so these I'm gonna. Do I have some time left? Oh, okay. Okay, thanks. So here in this experiment, we wanted to understand the impact of the threshold and the prediction in our work. So for the left side figure, I'm not going to detail again, because threshold is something that I didn't really specify here. It's going to be too much for this talk. But on the right side figure, of course, we don't always predict right? And we wanted to evaluate what influence does it have if we predict wrong, which happens. It's the real world. Sometimes we predict the wrong event. And as you see here, even for like 40% of wrong prediction rate, which is, as I showed you, like the accuracy, it happens it doesn't happen much. But even if we have 40% of wrong prediction rate for a cluster size of 800 pods, we are still below what OPA gatekeeper does. We stay like around 140 milliseconds, which is acceptable. Okay, some concluding remarks. To summarize, so we designed and implemented ProSPEC, so proactive security policy enforcement tool for container environments. We integrated it with Kubernetes and OPA gatekeeper and run some experiments. We use the novelty here is that we use a predictive model to predict the event and perform the computationally injustice steps in advance. And so that allows us to have a very low delay at runtime. And we around 10 milliseconds for each of the pods. That's the performance that we reach. Few limitations quickly. It still requires some manual effort to identify what events are critical. We need to input like the security policies by hand. This is not done automatically, and that's why we still need some experts to write the security policies and to configure the tool at first. And we would like maybe to get rid of that, try to automate that process. And also our model is not retrained, it's not also fine-tuned with dynamic changes, meaning that when you are at runtime, maybe you would like to do some continuous learning, try to with the new event that comes in, maybe you want to change the model and try to change your prediction based on the runtime. So that's something that we would like to do. You can have a look at the project webpage, and if you want to have a look at the CD, you also have the GitHub. Thank you very much for your time.
Questions? talk.
I would have a question online if there is no one.
We just have a question in the room. We're going to do it first. All right. So yeah.
I was just curious if you are an attacker that knows that you have this defense mechanism in place, a predictive accelerator for enforcement. Just your thoughts on what you might do to circumvent this problem.
Absolutely, yes. So I think you want to talk about like adversarial behavior. So meaning that an attacker could actually try to trick our tool in order to make us do some wrong predictions. So yeah, this is why we actually run the experiment that shows that wrong prediction have minimal impact on our work. So even if the attacker tries to make us do some wrong predictions, so for instance, he's going to make the same event a lot of times in order to make us change the prediction. Even with that, if we don't predict the right event, we just fall back to an intercept and check mode, which allows us to reach the same performance at least as the existing tool. But as you see here, even if the attackers makes us do 40% wrong prediction rate, which is a lot, you see that the response time is still lower than what the existing tool have, because we still have 60% of right prediction. So yeah, that's my answer. And you don't know that it's wrong ahead of time. You just when you have an event, you're going to predict the next one. And if the next event, when it happens, if it's not the one you predicted, then you know that you have a wrong prediction. And actually, this is fine. You just, as I said, you just fall back to intercept and check just like any regular tool would. So yeah.
Questions from online participants?
Yes, if you have question online.
Yes, I have one. It's more like an understanding question. You talked about the race condition while creating the containers. Your new model is just reducing the time for the race condition, and this is still there, or is there also a solution to solve the race condition completely?
So yeah, very good question. So yeah, we solved the race condition completely because we actually wait for any event to. We actually wait for the pre-computation to be done in order to process the next event. I don't know if I'm being clear, but there's two things here to prevent the CVE. Yeah, the only thing that we do is we don't we wait. Okay, just like we block when we have an event, we're just going to block it, verify, then take the next one. So this is what the OPA Keeper tool here doesn't do. They don't wait for the replication to be done before processing the next event. That's something that we do. Yes, so yeah, that's how we prevent the CV. It's actually not a big deal, but that's something that we can allow ourselves to do because we have the prediction. And so we know that we're not going to lose much time by blocking the no request, because since we have the prediction, we're going to have a very high performance afterwards. So yeah, this is why we can do it, and OPA cannot do it because they already have some performance issues, as I showed in the previous slide.
Yep. Thanks for the presentation and the answer.
No problem.
Any other questions from online participants?
If you have any other question online.
Okay, so if there is no other question, let us thank the speaker for the wonderful talk.
Thank you very much.